teenager, I actually started building off when writing Ellis. That's why I really like the idea of building genomes. And we started this synthetic project, where we've been really starting to work in what is required for synthetic genomes, like automation of design, scale of DNA synthesis, parallelization of methods, automation of verification of software. And then with the project now, we've been looking at biology, how to remove elements, unneeded features, auto up the genes, and adding recombination sites in as well, so we can investigate the plasticity of the genome. You can see a diagram of that scramble. And now, most of us on the synthetic project working on chromosomes, even Imperial working on chromosome 11. We're now investigating biology with these synthetic chromosomes, exploiting strategies, doing things like scrambling the chromosomes in industrial conditions, being able to determine scramble events with things in this case, for example, sequencing here to see inversion teleplex to improve phenotypes for events. What I really like about SC2 is its technical challenges, the ability to understand the fundamental biology, and then be able to exploit that in different ways. If we think about how to scale mammalian genomes, then we're going from things like, in our case, 2/3 of a million base pair chromosome. If we choose the smallest chromosome in a human, that's still 50-fold increase in what we have to do. So there's a lot of barriers there. So just as a pitch for potential pilot projects we might do out of Imperial College and in the UK, are things such as SC2 scale regions, areas between about 500,000 and 5 million base pairs in size, in sort of loci within the genome that are industrially or medically relevant. And we want to do the sort of things we do in SC2. So we want to remove destabilizing elements and instead put back in things like LOXP sim sites that allow us to still do the plasticity of the genome, but under controlled conditions. So we just brainstormed a couple of candidate regions. The first one, fortunately, is in a non-essential chromosome, Y chromosome, as was discussed earlier. And this is a section, 3.5 million base pairs, called the AZF locus, which has multiple repetitive and large palindromic regions that naturally cause a lot of deletions and rearrangements of this region. And why would we want to tackle this and reduce it down so it doesn't rearrange, or that it can rearrange on cue? Well, that's because deletions within AZFc are the biggest cause of male infertility, because you get different sperm morphologies appearing that can and cannot swim. And so you can imagine ways where you could understand how these different changes lead to the different morphologies and how that could be addressed. Now, this wouldn't be something you could necessarily do just in a cell line, because to get a sperm with full growth and morphology, you need to have an organoid as a minimum to be able to generate this. So this would certainly need to be something we might want to consider more to be done in a mouse model, where a lot of progress is being made in sperm generation in vitro. Region 2 is a big region that many of you have probably already thought about as a region you might go for, a plastic region of the genome with a lot of diversity, a lot of modularity, and that's the MHC locus. And particularly we were thinking about class 2 region of the MHC locus of the human genome. But when myself and Paul Fremont went to speak with immunology experts, John Trousdale at Cambridge, he said, oh, you know what would be great? Don't go for humans, but go for chickens. So sorry, Human Genome Project Right, but we might do Chicken Project Right, because the chicken B locus is naturally a minimal MHC. It can do everything the MHC requires in a chicken, and it's only between 90 or 300 kb, depending on who you talk to. And so you can imagine a project to synthesize this region, building and testing minimal versions of the MHC locus that effectively is like this chicken locus, in order to understand what the MHC genes do, what the regulation is there. Or alternatively, we could synthesize the chicken MHC as it is, but introduce into that the inherent ability to easily insert extra genes, extra diversity. And you can imagine biotech and health-related applications with that. Make chickens less prone to things such as avian flu, for example. Interestingly, the reason chickens have much smaller genomes in general is because as flight emerged from dinosaurs, there seemed to be a metabolic cost about having too much DNA and all of the equipment for that. And so they believe that the genomes have reduced to allow flight. So we may be inadvertently, if we expand the chicken MHC, we may be going backwards in time. And So we don't necessarily want the project to end up being something like Jurassic Park with dinosaur chickens. But anyway, there you go. And this car is just around the corner. So if anyone wants to go see that today, that's me today. All right, thank you.